So, okay. So, all right. So, welcome. Welcome to the Wazero Party 2.0. That's right. Let's see if the clicker works. There we go. There we go. Okay, so this will be the plan for the night. I'm going to do an introduction and I'm going to explain what this release is about. And then we have Mohammed, and we have Shabad, and we have Sven, Kevin, and Ron at the end. Dulcis in fundo, as we say. And so this is about Wazero 2.0. New features. Well, as I mentioned in the talk, they have to bring immediate value, and one of the features that brought most immediate value, even though it took a while, was a multi-pass optimizing compiler. It was a feature that was long requested by our users. I wonder if this is actually recording. We'll see. But it was so important not to break people that this is actually 1.7. So let's ship it. All right. So we're going to do the release live again. All right. So Kevin, push the button.
All right. 3, 2, 1, go.
It's done.
Right.
It's online. Yay. But how do I enable this wonderful piece of software? So these are the lines you need to change to enable the optimizing compiler.
Can do.
Dan, I'm not a Republic serial villain. Do you seriously think it explain my master stroke if there remains the slightest chance of you affecting itself? I did it 35 minutes ago. Actually, we just did it. So you don't need to do anything. We did it a few days ago. It's the default. It's the new compiler is just there. And you
Very well read.
No changes. So with 0.1.7, it's a release that upgrades like a minor, feels like a major.
Nice.
So I'm going to explain to you, if you're interested, how the optimizing compiler works really quickly. So usually this was just basically 2 steps. Now it's a bunch of more steps. The new compiler draws from several compiler architectures such as PA, LPM, and goes on compiler. So there's basically 2 large phases, front end and back end. Front end does stuff that is multi-platform and platform independent, and the back end it's platform dependent. So if you're not familiar with the concept, the way it works is that you get WebAssembly, you translate it into an intermediate representation. In this case, it's called an SSA. The reason why it's called an SSA, I'm going to tell you. In practice, and in order to be short, because we don't want to do a class and compiler design here, the idea is that you have these basic blocks, and you break down your function, in our case, into these basic blocks, and the basic blocks are broken down at the boundaries between control flow instructions. And instead of having control flow instructions, you have edges in a block. So every block that contains sequence of instructions that do not change the flow, and instead of having the control flow as an explicit flow, you have edges, and that will be your twist. And it's called an SSA because that's called instructions and single static assignments. What that means is that the variables that occur on the left-hand side and on the right side only occur once, basically. They're only defined once. So instead of having x everywhere, we just do a rename, and then x becomes x1, and the following line x2 gets assigned to x1 minus 3. By the way, it's not important. The example is not. So that's how it works. And the reason why we do this renaming is that it's easier to do analysis later. All right. So how do we do optimization passes? So the reason why we do SSA is that it's easier to do optimization passes. So to give you an example, we have a very simple example, very simple C program here where you have a couple of assignments, and you have an expression, mathematical expression, and if 0, which apparently it should be a constant, compile time constant that it gets evaluated in this case to 0 for the enabling or disabling debug, and then there's a print in case this is true. Otherwise, it does. So first you could have passes like that code elimination, and in this case, you know statically that since the debug variable, the constant evaluates to 0, the entire block can be eliminated. So this won't even, when it gets translated into the control flow graph, we basically are eliminating edges and this node because it's irrelevant, right? And then you can do other passes such as constant propagation and constant folding. Like you know that A and B and C are only used here, so you don't have to do properly evaluate at runtime. You can do the evaluation at compile time by substituting A to B, A with 5, B with 6, so on and so forth. And basically all you get at the end is the C, which is a constant expression that you can evaluate to compile time, or build time, whatever. And so basically substitute that with a constant. And since this constant is only used in the return statement, then you can just return the constant. So this entire function has been folded into a constant. Okay. And the backend, what you do, so what I didn't really say at the beginning about our SSH, our running example. Our running example is doing add between two numbers and then subtracting another number. Okay, so it's simple. And so this gets translated to this SSA, where instead of having a stack-based instruction for Wasm, in Wasm we have instructions that look a little bit more like triples, like assembly-like instructions, and this is our intermediate representation. And we, instead of having like implicit values on a stack, we have proper named values. Okay, and they occur only once. Okay, so once you have the SSA, you can do these further transformations. Like for instance, the first thing that we do, we can translate this instruction to a sequence of instruction in assembly. In this case, I'm using ARM instructions. The translation in the case of ARM is pretty straightforward. These are 3 values, and there's an operand with the results, and then there's an operand. And that gets translated pretty much the same thing, except as you can notice, that there are new identifiers here. We had before V2, V3, now we have W with some high numbers and some question marks. What that means? Well, the thing is, real machines have a finite number of registers, but you don't really want to deal with that immediately. So what you first do is you just invent fake registers. Let's say I have an infinite number of registers. So in the case of ARM, we have 31 registers for 64 bits, but you have the 31 register, and you have 64 bits views and 30-bit views, and you can address them by using the right name. And then you have some other special purpose registers, such as a step pointer, problem counter, and then you also have 32 Cindy register, floating point registers. So you just, in our case, we are using just integers here. The phase of register allocation maps these registers that are virtual to real registers. So it's a procedure that tries to fit whatever the register you actually have into the virtual register that you created while you were generating this intermediate code. So after register allocation, this is what you get. And as you can see, now the numbers make some sense. Okay, there's no longer a question mark. All right. And at the end, what we do is, well, we finalize. So we add a bunch of stuff in order to, prepare the system to actually jump into the execution and stuff like that. And then we encode. So we assemble the instruction by following the specs, and we get stream of binaries that then we can execute. And that's how it works. Other notable features that we're shipping with 1.7, the Wasm thread spec, which, as we know, is not really about threads, but mostly about atomic operations, mostly, and sharing memory. And RAG, who's one of our contributors, needed that in order to support cross-compiling some C modules. So they are not really necessarily using threads, but did use atomic operations. So that's one of the reasons why we accepted that. We introduced that. And then snapshot and restore is a mechanism that's new. You will read this on the release notes if you want. And but it allows you to implement stuff such as an emulation for exception handling. And obviously, an experimental feature is Wasm I. Obviously not. All right, and that's pretty much it for a 1.7 release. So we can continue with our first speaker. So let me share.
Thank you very much for having me. I'm very excited to tell you about our journey with Wazero. I'm Mohammed Aziz, and I'm from Calypso. So Extism is a general purpose plugin framework that's designed to be really easy to use. It's implemented in Rust, and it's basically most of the other languages the case wrap the Rust SDK through CFFI. Extism provides a number of additional benefits on top of runtime like Wasm time or Wazero. It defines a well-defined API that allows complex data sharing between plugins and the host. It allows you to easily load Wasm modules from a URL, from a file, or from memory. And one of the most important bits is that we provide idiomatic and natural SDKs and PDKs for over 15 languages that allows us to bridge gaps between all of these languages. And we also provide a number of other benefits as well. So this is an example of a Go plugin that uses Extism to run a Wasm. Sorry, this is an example of a Go app that uses Extism to run a Wasm plugin. We define the source as a URL for the plugin, and then we initialize the plugin, and then we get some input data, and when we call a function called count vowels, and we pass in the data, and then we get the output of the call, and we print it. So Extism's API is very simple. It's bytes in and bytes out. This is the same example, but in JavaScript. If you notice, while it mostly looks the same, there are some differences. That's because we care a lot about each SDK being natural and idiomatic to the language itself. This is the same example in C#. So previously, the Go SDK also wrapped the Rust SDK through CFFI, through CGO, but that had a number of problems. One of them is that using CGO raises the barrier for contribution from the community. It makes cross-compilation tricky, and it also removes one of Go's most important attributes, which is single binary distribution, because you have to also distribute a large shared binary with your application. So the solution was to use a Wasm runtime that's written purely in Go, such as Wazero, and porting Extism to Wazero is easier than you might think. All you need to do is parse and load Wasm modules from a manifest, which defines all the different sources. You also have to manage memory allocation and freeing, and you also have to define about 30 PDK functions for the plugins to use. And you also have to initialize host runtimes for languages that need a little bit of extra care, and have the ability for users to define custom host functions. Now, you might think, Muhammad, this is not easy. This is a lot of work. But we have something called the Extism kernel, which is implemented in Rust, and it's compiled to Wasm, and it's shared among almost all of the host SDKs, and it's responsible for memory management, function call, input and output, and almost all of the PDK functions. So all of these are implemented in Wasm itself and used by the SDK. Now, we had some challenges when porting Extism from Wasm time to Wazero. That's because some of the concepts don't match 100%. One of the biggest ones was that Wazero doesn't have a linker. And that was a problem because while the kernel provides most of the PDK functions, there are a few functions like HTTP calls, configuration that the host itself needs to implement. So what we came up with was a solution where we basically wrap the Extism kernel module inside another host module. So in Wazero, there are two kinds of modules. There is a normal Wasm module that's loaded from a Wasm file and cannot be edited. You cannot add functions to it. And there's a host module where you can implement functions in Go and add to it. So what we did was we basically load the Extism kernel as a normal module, and then we have another host module that wraps the Extism kernel module and basically redirects most of the functions to the kernel itself, while also adding a couple of additional functions like configurations and HTTP requests and variables. So this is what it looks in code. We pass in the Extism module. This is the kernel, And then we build a new host module under the namespace Extism :host/environment. And then we basically wrap all of these functions that are implemented in the kernel, we wrap them in the host module. And the host module redirects all of these calls into the kernel. So what's next? If you are interested in trying out a few examples, go to extism.org. All of this is open source. You can check it out at github.com/extism/GoSDK. Contributions are always welcome. And if you have any questions, please join our very active Discord server at extism.org/discord. Thank you very much.
All right. I hope everyone is able to hear me at the back. So I gave a version of this talk last year at Cloudnative Wasm Day at KubeCon. So if anyone of you have probably seen, you might be aware of what I'm going to present. But yeah, primarily just talking about debugging. So of course, there was a really nice session today by Ralph and Natalia around how you can really navigate different kind of strategies towards debugging by taking examples of like Rust programming with C, C++. But I think like they mentioned that they were not able to build in time like a proper Golang debugging. But yeah, I mean, today we are going to be exploring what is there in store for us. And in case some of you were not able to attend that session, I'll definitely recommend all of you to visit that particular session once the recordings are live. But yeah, if you can look at today, like the overarching picture of WebAssembly, right? We have a number of different runtimes. We have more than 20 plus languages that have support, or the tool chains have support to compile your language code into WebAssembly modules and run them. But we don't really have a standardized proposal for debugging. We have one that was recently released for garbage collection, so that's pretty good. So essentially, what that means is that every single WebAssembly runtime has kind of adopted or is trying to adopt their own implementation of trying to debug, right? Now, whether it's through command line debugging, printf, using like printf, or going ahead and using your standard debugger or LLDB. And what that essentially means is that when you're trying to compare between different type of strategies, a lot of times when you're trying to run the same code inside of different runtimes or using different approaches, trying to debug, you'll get different results. And that's also like shown today in Ralph's demo where they were trying to like debug same C++ code with the help of LLDB and the general debugger, and it gave like different kind of responses. So look at what are different ways in which we are kind of debugging WebAssembly today. So of course, like you might want to use like print line debugging, which of course is a very standard way of like also debugging your standard software, but it can be a lot of time consuming. Then you might want to just do the testing of your original source code, which of course does make sense that in case there wasn't any issue during the translation of your original source code into the WebAssembly module, you might just want to have a look at, okay, is there any issue in my official like code? And I mean, it's a logical thing to do, right? If your original source code has some issues, it's better to like just debug that. And then of course you have your standard debugger. These are tools that allow you to run your WebAssembly programs, and then you can again put in checkpoints and try to see if there's an issue. Like you can look at the buffer array size and all. So those are great. Now, of course, if you're using something like WebAssembly on the browser, you have Dwarf that allows you to kind of do debugging inside of the browser itself if you're running it with JavaScript. And then, of course, we have more of not really debugging applications, but more towards profiling and tracing with tools like ModSurfer, Observe SDK. And I actually got to know about from Nord Squared about their application that they're very soon going to be open sourcing. That essentially allows you to basically take your WebAssembly module or your component file or from the registry and just get to know all of your input, output, import, export functions, and just get to see like a wider vision of like what your module really has. And they have some kind of capability of being able to see, okay, like if there is a certain export function that actually is is crashing or failing, so you'll be able to at least understand what particular part of your module might be giving that or throwing that error. Now, of course, like different runtimes, as I mentioned, have different approaches. So if we just kind of take a look at Wazero, right? So of course, Wazero is primarily written in Golang, or it's built for Golang applications. So of course, like most of the other WebAssembly runtimes, it does have support for dwarf. Like you can basically compile your WebAssembly module, and then you can use to emit or whatever logs you're getting from your WebAssembly module. So there's dwarf support, but also of course, since Wazero is Go native, that means a lot of the typical Golang debugging that you use for your programs could technically be applied. So whether it's like applying your breakpoints or checkpoints to your Wasm code. So I mean, of course, like not directly being able to debug the WebAssembly modules themselves, but at least the tooling to at least generate the logs and like trace your logs. Those will be possible with the help of the native Golang runtime that we're running it on. But of course, just a careful look at instrumentation, right? Now, of course, when we take a look at the standard way in which a WebAssembly module is formed in the first place, so you have multiple intermediate states. So you start with your source code, you have your LLVM representation, then LLVM IR, and finally into your WebAssembly module. And now what happens, of course, is that since you're shrinking down the size of the WebAssembly module, you end up losing a lot of the critical information that you might want to use or visualize when you're trying to understand like what went wrong in my in my WebAssembly module. So I actually ran this idea through a lot of like folks that why not build a visualizer, right? Where you take your original source code and have multiple levels in between. Like you could actually take a look at the LLVM state or the LLVM IR state, because these are much more much more mature states, and you have like proper debugging tooling that is available to actually look at these particular states. But of course, since we are losing so much amount of information, it might not actually make sense to try to find like what might have been the cause of an issue if the source code itself was not correctly configured. So another alternative approach that we have kind of been exploring is with the help of I think it's called MLIR, which essentially allows you to take a look at all of your intermediate states and actually save that information. So right from your source code to your Wasm binary generation. That's also like one of the use cases that we could potentially look into to at least have all of the valuable information that is required when you are transpiling your source code into the Wasm binary. And of course, like in terms of like this instrumentation, right? A lot of the different tools will tell you what are the import-export functions, but they'll not go too deep into like what's actually happening inside of the WebAssembly module itself. So those are some of the areas where we are actually lacking when we talk about like instrumentation from an instrumentation perspective. And I think like that's where really tools like Mod Surfer and the Observer SDK, they really come in handy. So of course, like Mod Surfer is a tool that where you can just go ahead and take your original Wasm module, you put it inside of their front-end application, and it will give you a list of all of the import-export functions. In fact, like it will also give you some additional information using like Fermion and sites about your Wasm module, how you can import it inside of a JavaScript glue code. And I think like more importantly, talking about the Observer SDK, because I think like that truly is a much better implementation in terms of like tracing your application, because essentially what it's doing is that it's taking all of the different function calls or what is happening inside of your guest functions, and then you're basically collecting all of that from your host application, and then you're basically sending it out to an external agent like either Datadog or any other tool that you might be using for profiling your application. So at least that gives you a lot more insight into what's actually happening inside of your Wasm module as compared to some of the earlier approaches that were just looking at your import-export functions. So yeah, I mean, that's a quick overview of where we are at with respect to debugging. And I think like I just made this kind of quick slide to kind of look at what are the different approaches that we have today that I've kind of already covered, and what are the pros and cons in terms of like the debugging world that we are in right now. And of course, every single tool chain that we are using today and every single runtime will behave differently. And that's what the major issue is, that we don't really have cohesiveness when it comes to debugging. But I think like ultimately, I think like very recently we had the Bytecode Alliance special interest group for debugging. So you can take a look at that as well. With the idea really being that at least with this approach, we'll have a standardized set of APIs that can be then adopted by any WebAssembly runtime and then they can start to implement it across different language toolchains. So yeah, that is a quick overview of where we are exactly at the WebAssembly debugging, and yes, especially when it comes to like Golang applications, definitely check out the Observe SDK. There's a specific Golang SDK as well with the Wazero runtime. So of course, like if this would have been a longer talk, I would have probably given a demonstration of that as well. But that's it. Thank you so much.
And the others. There you go. Oh, great. Hi, I'm Sam. That's me. And I like to run WebAssembly in containers. I had lately a discussion on social media. So a container is a polyglot runtime with a sandbox. Why should you want to run WebAssembly inside of a polyglot runtime which is a sandbox? So good question, definitely. So even if WebAssembly comes with a strong sandbox, it's not completely free of attack vectors. Especially if you have your own host functions, you may mess something up, and yeah, something could theoretically break. With the approach of defense and adapt, you have redundant security mechanisms. For example, stacking sandboxes, like sandbox and sandbox and sandbox. Of course, security in depth is not only about sandboxes. It's just a very, very tiny piece of it. So there's the physical, the technical, the administrative level. So, but all of that is way too complex to, condense it in 5 minutes. So when you are talking about containers, they are not perfect sandboxes. You need to configure them correctly. You need to take care of your images, that you're not running as a root user. And if you have all those things done right, that theoretically the escape risk is as minimal as possible, may something happens like a CVE where accidentally file handles are exposed inside the container, and you need to patch your runtime as soon as possible because, there are theoretically escapes possible. So containers are not the answer for secure sandboxes. VMs are, way better sandboxes, but you have, I would say, a classical application running on hardware. You have your OS, and the application is running on top of it. No isolation. With a hypervisor, you have the virtual machine manager in between, which is abstracting your hardware away. And you have type 2 hypervisors like VirtualBox that are running on top of the application system, operating system, running a virtual machine. On top, you have another operating system, and you have your application. And in terms of startup time and performance, it's not equal to containers. But there are micro VMs like Firecracker, like QEMU, KVM, and they are pretty fast in startup. The only question is, what operating system are you running on your micro VM to have a fast startup time and performant application? So a unikernel. You don't have a full operating system. You only have a kernel, and that basically is as small as possible and don't have even user space. So you press everything your app has together. From configuration, application, all your shared objects and third-party libraries, the parts of the operating system you need, you press it all together in one image and throw it at one of the micro VMs. Good idea? But you need to have all the dependencies in place. You need to have a build process that is building that. And the more dependencies you have, the more complex this build process is. If only there would be a WebAssembly runtime with almost no dependencies. Okay, so for Unicraft kernels, which I'm using here, there is already a way to build Go Go applications, which is a nice thing. And as you may know, creating an WebAssembly enabled runtime using Wazero is like a Go application. So you don't have more dependencies in it than a Go application, and it's as easy as a Go application. Okay, so this is our project setup. You may know it from the examples. It's an H calculator. So it's one of the examples. It's just invoking a simple function. The craft command is basically building an with BuildKit with Docker and rootfs, which is then used as rootfs on the kernel. It starts a local JMA instance, and you can just invoke it with localhost. When you see the command line interface is slightly behaving like the Docker CLI, so you can craft run, craft images, and this is our Docker file. We have. I can try it. Not sure because of the yeah. So this is the Docker file. The thing is, you can't just do a Docker build because the you can't statically link your application because it needs to be repositioned on the POSIX interface of the unikernel. So that's why you need to have this link mode external, and it's a little bit magic, but that's all. Besides the Docker file, you have and you have a scratch. So you're just putting what you need inside your rootfs. Besides the Docker file, you have a so-called craft file, and the craft file is then giving the information which rootfs, so from the Docker file you're using, and which runtime, and the base runtime already is capable of running Go applications. So same thing you can do with the cloud, and you see the boot time are 16 milliseconds. So it's a little bit comparing apple to pears when you are talking about containers, because when you start a container, it's downloaded from a registry. And here we already pushed the image to the cloud. It's already there, and they just need to start it. But 60 milliseconds is still something that can scale to 0 and is started up when the request is coming in. That's, I would say, an amazing user experience. So especially if you can turn it down if it's not needed. Exactly. The URL is just accessible in the internet. You can just call it. And yeah, thank you. That's a demo. Second last talk, Kevin.
Hi, everyone. I'm here to talk about building distributed databases with WebAssembly. So several times in my career, I've wanted a database that does exactly what I want and nothing more. And I couldn't find something that fit the bill. A lot of times these interfaces are very small, but they still have to be durable and consistent. They have to scale elastically, they have to function correctly, and they don't require a PHP to operate. That's a high bar to pass for something as simple as a service like SQS or something like that. So I created Logbin, which is an open model database platform and WebAssembly host runtime. Centered around distributed logs and state machines with Raft, and you can import new models at runtime built with WebAssembly. It has extensible capabilities and hopefully a unified management plane. It's layered, and we'll go through all the layers one at a time. So the first is DragonBoat. DragonBoat is a multi-group graph consensus cluster or consensus library built in pure Go. Unlike other graph libraries, which can only handle one state machine at a time, Raft can handle hundreds per host. It's used in production in a product called Matrix 1 that's marketed primarily in China, but it has impressive performance due to pipelining and batching, which are extensions of the Raft protocol. It uses gRPC internally. So if you start DragonBoat, you're going to get 3 hosts that are all in the same deployment, but they're not going to talk to each other or do anything. You need to have some kind of a priori knowledge to stitch these together to form groups, Raft groups. This is the sort of command that you need to run on all of the nodes at once in order to create just to bootstrap the cluster. So I created a cluster coordinator for Dragon Boat. There's a Dragon Boat festival in China, and they serve these little sticky rice dumplings called zongzi. So I named the library zongzi. So when you start the cluster, you have 3 identical machines. None of them have any knowledge that's different from one another, and you need to somehow form them into a cluster. Starting zongzi begins with a bootstrap protocol. So each of the hosts creates an internal gRPC API, and each host calls out to its seed list to begin cluster initialization or cluster restart. And it kind of does the right thing in each case. The result of this bootstrap process is the creation of a prime shard. So in Dragon Boat, every shard is represented by a uint64. So the prime shard is shard ID 0. It's a cluster registry that contains the current state of all of the hosts, shards, and replicas in the cluster. This registry is replicated to every host in the cluster so that every single node has a complete snapshot of the current state of the cluster. Does anybody recognize what this is on the right-hand side here? It's the matrix of leadership from Transformers, which is kind of an apt analogy because the leader of the prime shard is also the leader of the cluster. So there are several controllers too within zongzi. The shard controller is run 1 per cluster. So the prime leader is running that controller. The host controller is run once per host. The shard controller reads the state of the shards in the registry and then creates replicas in response, depending on the load on the host. So it does its best to balance replicas across all of the hosts in the cluster. This is very similar to a pod scheduler in Kubernetes. The host controller reads the state of the hosts and state of the replicas in the registry and responds to changes to itself. This behaves like the kubelet in Kubernetes. So rather than scheduling, or rather than starting containers on a node, it is starting replicas in Dragon Boat. So it's sort of like Kubernetes for data. These are some state transition diagrams that represent all of the valid transitions between the states. I don't have time to talk about this. The next layer is Hurricane. So whereas zongzi was responsible for forming a cluster out of hosts, Hurricane is responsible for forming a supercluster out of clusters. So you can think of 1 cluster per region. Hurricane is like the global deployment. It has resources and clusters. The cluster controller syncs the cluster state between the clusters, and the resource controller is responsible for responding to changes in the resource and then creating and updating shards. You'll notice there's kind of a directionality to the hierarchical control flow, and that's intentional. So you have global resources and local resources. Global resources have a controller. They create local resources create shards create replicas. I've just put a lot of dots on the board and not necessarily connect them, so it's okay to be confused at this point. This is a lightning talk. I wanted to get through that as quickly as possible to talk about the Wasm part of this. So every resource is an instance of a module, and modules can export state machines, controllers, and services. Logbin has adapters and extensions. In this case, we have 1 runtime extension, which is WAPC, which is WebAssembly procedure calls. After hearing the stuff about Extism, I'm probably going to look at creating a new runtime extension for that. There is a storage module, a storage extension called LMDB, and another cache extension for skip list. The extensions are registered through adapters with the WAPC runtime. You start the Hurricane cell register module. These are just byte slices of compiled WebAssembly, and then you define resources by giving module URI and a resource name, tell it what cluster you want it to be on, and then give it some resource tags. So this is what a resource module looks like as a tiny Go guest. The main function registers functions, which is how WAPC works. This is the entire main function. And we're going to look right now at the reconcile portion. So I mentioned that modules can export controllers, and they have 1 method, which is reconcile. This function takes a byte slice and returns a byte slice and an error. That's how WAPC works. It just functions on byte slices, which means a lot of serial. You'd really like to have a WIT runtime extension, but that's in the works. So you can see here, it is reading the shard count off of its tags, and then it is creating shards if they don't already exist. A real controller would be a lot more refined, and it would contain balancing and rebalancing and auto healing and all that. Does anybody remember this court case, Google versus Oracle? This is the one where the Supreme Court decided that interfaces are not copyrightable. So that to me is a business model. The EFF published this article at the time, and I would definitely re-implement an API. So if you wanted to, with this system, you could clone DynamoDB using only WebAssembly and then deploy it onto Login. Same with Kinesis or Redis or S2S. So that's the long-term vision. That's our mascot at the top left. That's Bingo. He's a chameleon. And if you're a platform engineer and you're developing a platform, and you have re-implemented the DynamoDB interface, you could migrate applications to use Logbin without even telling them that they've been moved from the real DynamoDB to something else, because the interface is the same. There's no need to create a new client. That's why it's a chameleon now. So the reason I came here is to get people to sign up for the newsletter. So if you all want to pull out your phones right now, go to logbin.com and enter your email address and press submit. I'd appreciate it. And that's it. So the other reason I came here is to express my gratitude to the Wazero team, because I think Wazero is awesome. So maybe we can end with giving a hand to the creators and maintainers and organizers.
Okay. Are we ready?
Go ahead.
Hello, everybody. This is Less Than Zero for all the 80s kids out there. I hope someone got that joke, or else it's very sad. All right, so I am Ron Evans, Dead Program on the internets, and I am a technologist for hire. Very subtle. That's very important to be very subtle in these things, I've been told. So I have a consultancy called the Hybrid Group. We're a boutique where we create the software that makes your hardware work. Done a few little projects for companies along the way, like Intel, Sphero, Pebble, Particle. So, we've been behind the scenes with some very smart people carrying their water and doing the best we can. So, but we do a few open source projects you may have heard of. One of them that we spend a lot of time maintaining is something called TinyGo. So, but kudos to the TinyGo team members who do a lot of amazing work for the community and all the great people who contribute. It's fantastic. So this is supposed to be the Wazero 2.0 launch party. It turns out it's 1.7, so I'm kind of sad. At the same time, I'm kind of relieved. I'm like, I didn't even know there was a 2.0 branch. So so this is kind of a relief. So this is about WebAssembly on microcontrollers, and why is always the question. I did mention some of these reasons earlier today. Hardware devices that are extensible, application-specific APIs for hardware. That way, if you're building set-top boxes or video games, devices that need updating. In other words, every device ever made. No, it's perfect. Really, ship it. And device code that's portable. That's why a lot of us are really interested in Wasm. Actually doing this, though, has been extremely difficult. Even though there's been a few projects that have run Wasm on microcontrollers, they've generally cheated. Things like Wasm 3, where they actually compiled it to native from the Wasm, which is an amazing hack. Actually, a great project. But now we've got Mechanoid. So Mechanoid is a framework for creating WebAssembly-based applications on embedded devices, IoT type systems. And it's written, of course, using Go and TinyGo. You can write modules in any language. I don't actually have any written in any other languages right now with me to demo, but it can be done. I've seen it. It does work. Batteries included, because we really like the idea that you've got everything you need to get started. You don't have to go on a scavenger hunt on the internet to try to find the packages, crates, or other increment of code distribution that's got the one magic function you need. And it's built, of course, on open source. TinyGo, as I mentioned, and the amazing Wazero. Could not exist without Wazero. I will say that. We also have a cool new package introduced by my colleague and collaborator, Graham at Orsinium Labs, called Wipes. We'll see that in a minute. So embedded systems are microcontrollers that are 32-bit processors with very limited amount of memory. And luckily, TinyGo runs bare metal on hardware. Somebody said define bare metal. Let me define it. No actual code that's not implemented in silicon on the microkernel, on the actual die of the chip you're using. That is actual bare metal. Everything else is not bare metal. Okay. Designing a line in the silicon. That's me. All right. No operating system, in other words. So how do you actually do anything? Well, with Mechanoid, we have to provide some mechanisms, if you will, to do these things. Your application talks to the Mechanoid engine. We can then use different Wasm modules and have them communicate with different hardware devices. The way we do this is the engine has an interpreter interface, and that interface can expose any of the different interpreters we support. Currently, the default is Wazero. We could add others. There is one other that we've got. It's called Wasman. It's kind of a toy. The only thing it does well is not use much memory. But other than that, it's quite hacky. So we only use it when nothing else will work. But we have something called the file store. You're probably wondering how you have no operating system. Where do you actually put any data? Does this mean you can only flash the hardware one time and then it cannot be updated? Well, of course not. What would be the whole point of this Wasm thing if that was how it worked? So I'm going to use the Tiny Circuits Thumby, which is a Raspberry Pi RP2040 microcontroller in the form of a very, very small thumb-sized gaming device. It's an ARM Cortex M0 Plus, which is what the RP2040 has. So it's basically one of the least powerful, I would say it's the least powerful 32-bit ARM type of die that exists. And it has 264K of RAM, though, which is quite sufficient for us to be able to do the things we need. And 2 megabytes of flash memory to store programs and data on. So let's actually take a quick look at the hardware. You saw it before earlier today, but it was probably pretty quick. Is this still working? Hello? Can you see me? Yeah. So you see it's really, really small, like incredibly small. It's got some buttons, a screen. That's about it. Is it on? Yeah, it's on. Okay. So let's see some code. First, let's look at the ping architecture. You saw this earlier today. This is kind of the hello world for us of Wasm. A ping module, which supports only one function, ping, which its implementation calls the pong function in the host. And then it outputs something on our serial port. We saw that before. Let's just take a quick look, though. It's the simplest module that could possibly work, I would say. Package main, go Wasm import. Thank you so much to Akile and for getting this in. Go export. This will be Wasm export real soon now. That's going to be nice. So the ping function calls pong. Pong is in the host. The main doesn't do anything because it's Wasm. So far, so good. So let's look at the file store application. So it's neat to be able to use the Go embed directive to put binary data directly into your application. But how do I update it after the fact? Excellent question. I'm so glad you asked that. So let's just take a quick look here. We are using embed. I'm not sure why. I think that's actually a mistake. Because of the underline, that could have been removed. So I'll take that out. That's not needed. But we've got the Mechanoid engine, the Mechanoid interpreter interface, and then wipes. So the first thing you do when you're using Mechanoid is you create a new engine. In this case, we tell it to use the default interpreter, Wazero, and we tell the engine to use a file store called FS. Now we init the engine, and then we're going to define 2 different modules on our host using wipes. One is in the module name hosted, and that's our pong function. And the other is in the namespace module env, and it's called Ola. That's just for a hello world type actual hello, but we're not going to use that today because of lack of time. But we set our modules, and then we're going to start up our command line interface. Now keep in mind, this is actually running, it's going to run on the Thumby. Yes, we're going to actually access the command line interface off of the serial port, executing on the Thumby, thanks to Wazero. All right. Because, I mean, every tiny little device needs a CLI that you can access directly from the device itself, doesn't it? I mean, I think so. So here's our Pong function. It just says Pong. Here's our OLA function. It just basically doesn't do anything except display the message. And then let's take a look at, oh, wait, there's one other thing that is interesting in there, which is when we are using it running directly on an operating system, we would have to use the file system on our actual machine. But since we're running bare metal, we're going to use the, whoops, go away. The way we're going to do this is we're going to use one of the capabilities that's built in the Mechanoid, which lets us use the Flash file store. So Mechanoid has capabilities built in thanks to TinyGo, which lets us use the excessive flash memory on our chip, the extra that's beyond the program we just put on there, as a file system, okay? And then we tell it that the start of that data is where the flash data starts, and the end of that data is where the flash data ends. And we're going to mount it using something called little fs. So little fs is a file system. Oh, wait, there's one other thing we have to see. This is too good. So let's actually see the CLI implementation. So remember, this is running on the microcontroller. This is not running on my machine. I'm going to access it from my machine. So we use a bunch of Go standard library packages. And here are the commands that we can type in. ls block, we want to see how much the flash storage is. Load, which is going to dynamically load one of the WebAssembly modules off of that flash memory. Save, as you might guess, that allows us to save a flash module that we're going to move over to the device using the serial port. I'm going to copy those Wasm files from my computer to the device using the serial port. We can remove them, run them, halt them, and then we can then call ping on that loaded module or hello on the other loaded module. So we just have some code in here in your typical TinyGo embedded code. And once we actually get the command, we run it. The one that's really interesting, you can see our ls function is run. Where is it? Here we go. So the run function basically takes and, well, first let's look at load, now that I think about it. Here we go. So what load does is it takes the name. If we were to type in this save and some name command, we would then be expected to upload the text, which that text is the binary data. Now, that's a little inconvenient, just because you'd have to like type this command, you have to know the size of the file and command C out. So one of our contributors gave us a little Go program, which already does this for us, opens the file, sees the size, sends the command, and then sends the data. So that's how I'm going to actually put it on there. Then we can load that into the file store and then load it into the interpreter. So then we're ready to execute it. All right. And then running it, we're already loaded. The module is loaded. So all we have to do is say run, and now we can call that ping function on it. We can execute that off of the instance and then keep track of the count. Here's call ping. Make sense so far? All right. So let's see this in action. Because, you know, proc is free. And so is open source, as it just so happens. So I really like make. So I'm going to say make file store. That's going to build the modules. They're not going to copy the modules, though. It's just going to, these are some modules I've predefined. I'm just going to build them and then leave them on my computer's hard disk. They're not on the machine that I'm going to actually run them on yet. I'm about to copy them over. So this is the Mecha command line tool. It's part of Mechanoid. It's got a few different commands. One of them is Mecha Flash. And Mecha Flash actually compiles, builds the modules, compiles the executing code that you're going to run on the microcontroller, and then flashes it on the microcontroller all in one step. That way, you don't have to, you know, first build your modules and then build your code and then flash it on the device. So if it all works, you can see here, the modules it builds are really small. The ping module is only 9 bytes in size. Like, you know, I'm not sure we can write a Wasm module that's smaller. I mean, maybe someone else here can. We can discuss that later. And then here is the actual application code. And here's my command line interface on this device. Okay, this prompt is coming from this device. So let's see what we can do. First of all, let's see how much memory we have available for storage. So the flash data starts at 1006 F1000 because up till that point, from the beginning of the flash memory to there is where the program we're running on this same device is. Okay, so here's the program, and then here's the spare data. All right, are there any files on it yet? Oh my God, there are files on it. Well, let's remove those so that you know I'm actually not lying here. So we say hello Wasm. We'll remove that. Oops, rm hello.wasm. Okay, it's gone. So now we'll rm ping.wasm. That's gone. Okay, no data. We good? All right. So now I'm going to Control C. It's still running. I can use the mecha monitor command. What monitor? And I can see there's still no data on there. All right. So far, so good. All right. So now I'm going to run a make command, which is copy files. So copy files is going to run that little Go program that was contributed. And it's going to tell the command line interface, it's just going to send save, file name, the size of it, and then copy it on there. So now if I use Mecha Monitor, go back here, and I ls, you see there's the files. Okay, those files were not on there a minute ago, were they? So this is dynamic loading of Wasm modules when, after the time, we could be doing over-the-air updates. We could be putting this on there through Bluetooth, through Wi-Fi, through a lower WAN update, through the serial port, however we like. All right, let's load and run one. So if I say load ping, so now the module is loaded. So now if I run it, it's running. Let's call it. I have a ping command, and let's say ping 10. So that's going to call the guest ping 10 times, one after another. We should also see the guest call the host pong function. So it should say ping pong 10 times. Let's go. Whoa, that's pretty quick. These things are not bad. You can even play games on them. All right. So that basically concludes my demonstration. It actually does work. You could do over the updates. You could do most of the things you actually need for real embedded hardware development in the modern era. And it's all thanks to Wazero. So join, and Mechanoid. So join the evolution, be one of us, or be one of the humans fleeing from us. I mean, I'm a cyborg, so I'm not sure which side I'm on, honestly. But it's been a really exciting journey, and we're really just starting it. So thank you so much. Mechanoid.
So that was a wrap. So thank you guys, and so just enjoy the food.